In this lecture, we will talk about the corrosion kinetics. Kinetics is important as it allows us to quantify the corrosion process and also predict the material loss with time in the future, right? Now, one of the major concepts in corrosion kinetics is polarization. And before I explain you what polarization is, I would like you I'd like to remind you about the one of the examples that we studied early on in this module, and this was the dissolution of zinc in hydrochloric acid. Allow me to go back to the sketch that I've done prior. So I'm looking at this particular sketch, and I will remind you what the case was. We had a single electrode zinc that was placed in hydrochloric acid, and we knew that the corrosion occurs, and there are two reactions that are associated with that process. We had oxidation of zinc, right? And this is the potential that is associated with this reaction. And if you're wondering where that number comes from, this just comes from this particular table where we have the standard electrode half cell potentials listed for various metals and reactions, right? Now, and then we also have a reduction of hydrogen, right? Or hydrogen evolution, and we have a potential associated with that reaction. Now, each of those reactions, they happen at either local anode, that's for your oxidation, or local cathode, which is relevant for your reduction. And as we see on the slide, is that each of these reactions have a unique potential, right? And they're different, negative 0.76 and the zero. But we also know that these two reactions, they occur simultaneously on a metallic surface, right? On the same metallic surface. Metal is an excellent conductor, so it is impossible to maintain these two different potentials on the same metallic surface. Since it's a conductor, there's got to be an intermediate number that connects these two, right? Due to the fact that the metal is an excellent conductor. So if I am to depict it another way, let's say I am looking at this point B, or perhaps I shall start with point A. I'm looking at this point A, and you will see that this number is exactly as 0.76 volt, right? This point corresponds to your equilibrium potential and this current density of zinc, right? Now, we also know that this point B, which is a 0 point, this is going to be the equilibrium potential and current density of hydrogen. But as I stated earlier, as these two reactions, oxidation and reduction reactions occur, they have to occur at a certain intermediate point, just due to the fact that they are happening at the metallic surface and it's a perfect conductor. So we can't maintain this differential on the metallic surface, right? And so what's going to happen if we are to actually depict it, right? So we would need to find a point in which these two are identical. And this is what we call E sub corrosion, and there's going to be also a current associated with it. We call this intermediate point. Now, that potential is going to be the real potential that exists on the metallic surface, and that potential is the one at which corrosion actually occurs. Now, and we clearly observe this displacement, right, of the electrode potential from the known equilibrium values to this intermediate point. That displacement is called polarization. So if I am to go by the full definition, polarization is a displacement of electrode potential from their equilibrium values. And in here we are referring to values A and B that we've seen before, right? Which is going to be negative 0.76 for zinc and 0 for your hydrogen electrode to some intermediate value, right? That is the value right here. And the creation of net current flow, right? Now, polarization can be classified into activation polarization and concentration. Um, they are very different, and the reason you would like to understand each is because the knowledge of either activation or concentration polarization allows you to tailor the corrosion process. And in most scenarios, I will give you an example in a little bit. So activation polarization, this in this particular process, the electrochemical reactions, and I'm referring to the reduction of metal, right, to the oxidation of metal and the reduction of another component. It could be hydrogen, right, or it could be also metal. Such electrochemical reactions are controlled by a slow step in the reaction sequence, meaning that there is a critical energy that is required to surmount the barrier associated with the slowest step. And allow me to zoom in and explain you what I mean by that. So if I am looking again at the example of zinc being corroded in hydrochloric acid, I also realize that, okay, so for this process to happen, and I'm going to be looking at the reduction process, right? The first step is that the hydrogen ion has to diffuse to the surface. Then the electron transfer has to occur. Then the formation of neutral hydrogen atom has to occur, which then bonds with or comes perhaps this, I'll mark it as 4 and 4, right? Which then forms as the hydrogen molecule, and eventually these hydrogens combine and then they leave the media, right? So I can take the corrosion process and I can break it down into a sequence of steps. Now, in the process of activation polarization, the the electrochemical reactions are controlled by the slowest step in the sequence. And there is a certain energy that is associated with that process, meaning that I have to supply that minimum amount of energy that will kick in that slowest step. And that slowest step is going to also control the reaction. Now, concentration polarization, and once again, I'll emphasize it, and it comes from the name. You don't really have to memorize it. Activation polarization, it is linked to the step in the sequence of the series, right? And then that means that there is a certain energy associated with the activation process, right? Because we know that polarization, we just looked at what polarization is, right? If we are to simplify it, it basically meaning corrosion process, right? We just know how it occurs, right? With the displacement of the potential from the equilibrium points. Now, activation polarization, it is controlled by the slowest step in the sequence, right? In the series of the steps that is associated with the corrosion reaction. In the concentration, it is all about the electrochemical reaction is controlled by the diffusion of ions. And one of the ways to keep in mind, you can either memorize the word diffusion or you can memorize the word concentration. It has to do something with the concentration. And allow me to explain it the following way. So we're looking at the example, and I want you to think of the reduction of hydrogen ions, okay? We know that this happens at the surface, right? It happens right here. And we know that these hydrogens, they have to be available to be reduced, right? And as they are actually, we always have an abundance of electrons. And as these hydrogens are consumed, right? So meaning that the moment this happens, this particular scenario happens, right? Once these hydrogen cations are consumed, that means that now the area is depleted. And so that means that now I need to wait for other available ions to diffuse into this space next to the surface of the metal, meaning that polarization in this particular scenario is controlled by the diffusion of hydrogen ions into the metal surface, right? And perhaps it's really important to give you an example right now that would make this knowledge useful, right, and practical. So once again, I can have you guys can also have both present, but the diffusion or concentration polarization, the one that is on the right, is perhaps very important when I'm dealing with diluted solutions. Because here's what happens. If I am to increase the flow rate of my corrosive fluid, in the activation polarization, nothing will change because there it's not controlled by the diffusion process. It is controlled by the slowest step and by the activation energy that is associated with a step. But in the diffusion process, if I am to actually increase the flow speed, I will increase the diffusion of ions and I will accelerate the corrosion process. And as an engineer, I can go backward, right? Meaning that if I wish to slow down the corrosion in a specific process, and I know that that process is controlled by the concentration polarization, controlling the speed may allow me to control the corrosion process itself. And this is why we want to be, whenever we encounter a corrosive media, we want to understand what is the primary polarization process that is happening in this particular case that we are considering. Is it activation or is it polarization? Because then it gives us, this knowledge gives us access to specific tools how we can control the corrosion process. Now, another very unique phenomenon that we should be familiar with in corrosion is called passivation. It's been known for more than 100 years and it hasn't been solved to this date. There are certain theories explaining perhaps what is actually happening, but it is still an ongoing research. However, we are already at the point where we are successfully using passivation in a lot of applications, not just within educational environment, but also in the industry. So passivation is basically a loss of chemical reactivity in presence of environmental condition. So what it means is that typically you would expect, and I will even give you a real example how passivation was discovered early on by Faraday. Let's go back to the example of zinc and hydrochloric acid. You drop zinc and hydrochloric acid and you instantly see the corrosion process, right? Zinc dissolves, hydrogen evolves, okay? Now, well, let's say if I am to take the tank, or let's say I have a glass, right, or container, glass container with iron, a tiny iron bar in there, and I have nitric acid, okay, highly concentrated nitric acid, okay? So what happens is that it's all the condition is almost identical to what you see with zinc and in hydrochloric acid, right? So naturally, you would assume that the corrosion shall kick in, and it's highly concentrated solution. But it doesn't happen. So nothing happens. You look at your iron, and the corrosion is minimum to none. You cannot observe anything. So what Faraday did when he saw it, he decided to dilute the solution. Okay? So he decided to dilute the solution, right? To see what's going to happen then, right? He tried to dilute it, nothing happened even after that. So what he decided then, it almost felt like the metal is protected by something. So what he did then is that he took, actually I don't remember, either he vigorously shook the container or he took a He scratched the iron oxide because it felt like the metal was protected. So he scratched the iron oxide, the iron, and what happened is that scratching the surface instantly kicked in corrosion. And then you see the vigorous bubbling, and then you see everything that you would expect to see when you drop a metal in most metals in acid. But what he discovered is that under certain circumstances, some metals can behave as inert metals, right? They would behave such as platinum or gold, right? And you would expect them to corrode, but they won't. And the idea is that we believe that the reason it happens is that there is a specific surface layer that forms on the surface of a metal that inhibits corrosion reaction. And there are two theories. That is oxide film theory, and then the adsorption theory. In the oxide film theory, basically the idea there is that there is a passive film, and that passive film serves as a diffusion barrier for the corrosion to occur. Okay. And that passive film is considered to be made out of the reaction products. Now, the adsorption theory says that the passive metals are covered by chemisorbed films of oxygen, meaning that the oxygen available in the solvent gets absorbed on the surface, and that creates again a barrier that doesn't allow corrosion to occur. And as you scratch it, the corrosion kicks in right away. Even though we cannot explain the nature of the films, the two theories that exist, the reason they exist, I'm not going to go in details, but there are studies that do show you that there is a potential that that film is made out of oxygen that is chemisorbed on the metal surface as a film. Now, the oxide film theory says that the passive film is a barrier made of reaction products. There's a study that shows that as well. In some examples, you can actually see the film, the film that is formed, you can visually see it, specifically when you have steel in sulfuric acid. But even though we cannot explain what exactly happens, luckily for us, the metals that exhibit this behavior are the metals that we commonly use in construction and engineering. And those metals include stainless steel, nickel alloys, titanium, and aluminum alloys. And this is why, as an engineer, and perhaps when you're doing your plant design or you're designing a process, whenever you have to deal with very, very strong oxidizers, right? I'm referring to acids. We often opt out with going something like stainless steel, right? If we have to. There are cheaper options such as polymers or ceramics, but stainless steel is a metal, yet we can use it for storage of highly corrosive fluids because it has this passive behavior under certain conditions, right? And I do want you to keep in mind these names of metals because we already developed a technology that takes advantage of the fact that the metal can have this passive active behavior. And what I mean by that is that it's a metal, so it should act as any other metal, meaning that it should corrode in acid. But we do know that under certain circumstances, the metal can actually have a passive behavior. And so if we can maintain that environment, that means that I can have my metal being inert to a highly corrosive environment, okay? And the way to actually represent that, you can represent this by the polarization curve. And what polarization curve shows, it basically demonstrates how the potential of a metal varies with current density. And I'd like to show you the following. So let's start. Let's imagine I'm at point A that I'm marked with red right now, and that is my equilibrium half cell standard potential for a specific metal. Doesn't matter which metal it is, right? Could be iron. Okay. Then what I'm going to do is that I can change the potential. And typically, for the majority of metals, if you are to increase the potential, right? Or if you make the potential more positive, right? What's going to happen is that the material will act as an active metal, right? And what it's going to mean is that the corrosion is going to increase, right? And you would see it with the increase in current density as well. But for some metals, at some point, even though the media inside, I'm creating an environment that is more and more corrosive toward my metal. But at some point, you will observe that there's going to be a switch, meaning that all of a sudden the current density will start dropping. And even though I'm still increasing my potential, right, my current density decreases, right? You would see that if I'm going this direction, the current density now decreases. And then at some point, I'm entering this region, right, where the current density is extremely low. And you guys know that corrosion, there's got to be the electron transfer, meaning that you should be able to see a certain current, right? But if a current density drops very, very low, that means that the corrosion is minimum, right? Minimum to non-existent. And then at some point, if you actually continue increasing your potential, right, then the material can jump back into this transpassive region, meaning that corrosion can accelerate again. And eventually you can make the material active again. So what that means is that certain metals can exist in these three regions, right? Almost all metals have this active, no, not almost, all metals, right? Almost all metals. All of a sudden, I started thinking of the inert metals, right? Almost all metals, they have this active region, right? Meaning that if you create a highly corrosive environment, then the material corrodes, right? And the current density increases, corrosion accelerates. But at some point, only very specific metals or alloys, they can enter this passive region, right? And then I'm referring to this area right here, which is going to be very important, right? Because as an engineer, later on, I will go in detail how people designed the system that allows you to use this knowledge to protect your metal. But what actually happens is that I can measure these two numbers, right? And if this is going to be my E1 and this is going to be my E2, and the difference is going to be the delta E, that means that if I am to maintain my material at this potential, right? If I am to connect it to my potential stat, and if I am to maintain my material, my pipe, my tank, whatever it is, if I am to maintain it at a potential within that range, that means that my material is passive and it will not corrode. And that is the beauty of understanding polarization and knowing that there is such phenomena as passivation or passive active metal. Later on in this course, once we go into learning how to control corrosion, this particular phenomena is going to be very important because it allows the metal to be protected by maintaining it at a certain potential at a certain potential. Um, it's not very common, mostly because it is expensive, and the system is pretty complex. It does require, it has a very high cost of installation. And then you can imagine that going out of that range will have pretty bad consequences, right? Because if we are to jump out of the range that we highlighted as the passive, the material becomes active, right? And that means that the material will begin corrosion. Now, many metals do not behave as galvanic cells due to passive films, right? Um, so meaning that in under certain circumstances, the metal will not behave the way you would expect it given the environment it exists, right? And this is why we need to experimentally define the galvanic series. And I'm about to give you an example. Now, the galvanic series gives us the cathodic-anodic relationship between the metals. For example, this particular galvanic series that I'm showing on the slide, I'm about to enlarge it so we can actually see more of it. This galvanic series has been measured for different metals, and that has been done in flowing seawater. Okay, and this is important. Now, typically, the galvanic series for every single environment, you would have to determine it experimentally, right? So the one that I'm showing you is only relevant for the flowing seawater, right? But what you have to keep in mind is that the galvanic series is always determined experimentally for every corrosive environment. How would that be useful? Well, imagine if I need to, if I am working with an aluminum alloy, right? Just as an example, this is an aluminum alloy, and you will see that the potential is in that range, right? So now I can instantly identify which metals on the list will be cathodic and which will be anodic. So for example, if I am to put in contact aluminum alloy and magnesium, this is going to be trouble, right? If I do not intend either to corrode, right? Because magnesium will instantly be more anodic with respect to aluminum alloy, and that means that your magnesium will corrode. So if I do not have the intention to corrode either of my materials, I would use this series to choose the metals that have similar potential to avoid the formation of a galvanic cell. Now, the reason I kept emphasizing that the galvanic series is generated experimentally because it can show you the data that you want predict, or perhaps you would predict the opposite. And for a second, I want you to look at the following. And specifically, I want you to look at the examples such as zinc and aluminum. And before we look into the galvanic series and see what happens in the flowing seawater, I want us to go back to see the standard potential on either, right? To see if I am to pair zinc and aluminum, which one is more anodic, which one has the higher tendency to corrode. Okay? So I'm going to go back in here, and I know that they're both negative. So zinc, I'll use this purple color right here. Zinc has a negative potential of 0.76. My aluminum has the negative potential of 1.66, right? So if I am to use just this standard electrode half cell potential, I would make a conclusion that my aluminum is anodic, right? Meaning that you would suspect aluminum to corrode if you ought to link these two. But let's look at the experimentally derived data and to see what happens here when we are looking at the zinc. This is your zinc, right? Right here. And then this is your aluminum, okay? So we will see zinc and aluminum. So we will see that now the difference is flipped, right? Your zinc is actually more negative, meaning it has a higher tendency to corrode. This is why every galvanic series, right, for specific corrosive environment, in this particular scenario, it's a seawater, is generated experimentally. But hopefully you understand how to use the galvanic series. I will be giving you some examples where you have a bunch of pipes connected, or certain pieces that are connected with each other, where you have to identify and spot the examples where some kind of insulation layer should be inserted to prevent galvanic corrosion. Now, the last concept is now that we understand passive such elements as polarization and passivation, we would like to be able to actually quantify corrosion process, right? And what I mean by quantification is I would like to know how much of material I'm losing, right? So that way I can account for the additional thickness, or I can estimate, I can replace the pipe before the pipe bursts, right? So the uniform corrosion of metals is determined by the Faraday's equation. And the equation states as following. This omega is the weight of metal in grams that is either corroded or electroplated in the aqueous solutions in time t. Okay? So then I is going to be your current flow, which we measure in amp. T is going to be the time in seconds. Uh, well, I guess it says right here. The M is stands for the atomic mass of metal, and the units are gram per mole. And if you, I will remind you that you can always pick that number from the periodic table, all right? N is the number of electrons either produced or consumed. And the F is your Faraday's constant, which is equal to 96,500. And the units are amp times second divided by mole. Now, we can also rewrite this equation. So you can either have this ITM over NF, or you can rewrite your current as current density times area. This area is going to be a cross-sectional area of where corrosion occurs, right? And we are about to see the examples to see how you can actually use it in real-time examples. And the rest will be the same, NF. Now, the last thing I will mention is that the corrosion rate is expressed in weight loss per unit area per unit time, okay? Or sometimes we can also express it as loss in depth per unit time, okay? Let's look at the first problem. So we're looking at a copper electroplating process. So this time, this is one of the processes where you're using the corrosion in reverse order, right? So I am corroding something, right? But I'm at the same time, I have a copper that is electroplated on something else, right? Now we're using the current of 15 amp, and perhaps I'm gonna write down the given values right in here. And I'm chemically dissolving a copper anode and electroplating a copper cathode. Okay, if it assumed that there are no side reactions, how long will it take to corrode, given weight is 8.5 grams of copper, from anode? All right, so I'm going to start with the equation, which is going to be ITM divided by NF. From here, I need to identify how long, right? I need to identify the time, meaning that the time it will equal to weight NF divided by IM. Now, let's start with plugging in what is known, right? So we're given the weight, 8.5 grams. I'm going to keep the units, times we're electroplating copper, which is going to, the process involves 2 electrons, times the Faraday constant, which is going to be amp per second divided by mole. And then I'm having current of 15 amp, and times the molar mass, I'm grabbing it from the periodic table, and it shows it as 63.55 gram per mole. Okay. Now, I'm gonna first start with units. I know that since this is time, my units should be seconds, right? Or if it's too many seconds, we will probably use either minutes or hours. But we need to make sure that the units actually make sense. Grams cancel out, amp cancel out, mole cancel out, and indeed I am left with seconds. So if I am to do the math, it looks like the time is 1,721 seconds, or it is roughly 29 minutes. So it takes about 29 minutes to electroplate 8.5 grams of copper. Now let's look at a bit more interesting example. We we have a mild steel tank, cylindrical tank of 1 meter high and 50 centimeter in diameter. Okay, well, let me draw it. So I'm looking at the tank like this. Okay, so I know that the diameter is 50 centimeters, and then the height of the tank is 1 meter. I'll use centimeters, 100 centimeters in diameter, and contains aerated water at the 60 centimeter level. Okay, well, that's important. I have an aerated water that is about, if this is 50 up here, right? So I have water at this distance, 60 centimeters. Now, this tank shows a loss in weight due to corrosion of 304 grams after 6 weeks. Times is 6 weeks. It would make sense to make a conversion right away, right? Because I know that I need seconds for my equation. 6 weeks times 7 days times 24 hours times 60 minutes times 60 seconds. That would give me a very large number in seconds. Okay? Weeks, days, hours, minutes, seconds. Done. Now, the question number one is calculate the corrosion current. Okay, well, if I am to begin with my equation, which is I m T N F, from here, the corrosion current is weight NF divided by MT, right? Now, let me plug in the numbers and see what I am left with. It's going to be 304 grams times, this is a mild steel, but I'm going to assume that this is a pure iron, right? And again, we're going to assume that this is a pure iron 2 plus. Under some circumstances, it is 3 plus, but I will prepare you for those circumstances. So it's going to involve 2 electrons. Now I'm using my Faraday's constant, okay? And I'm dividing it, since I'm assuming that this is a pure iron. Looking at the periodic table, the molar mass is 55.85 grams per mole times time, right? Which I already estimated earlier. So if I am doing this math correctly, I got 0.289 amp or 289 milliamp, right? Okay. And I'm running out of space, so I'm just going to make it slightly smaller, but still visible. Now, next question is, calculate the current density involved in the corrosion of the tank. Assume, all right, so now we need to estimate the current density. Now, assume uniform corrosion on the tank's inner surface and that the steel corrodes the same manner as the pure iron. Okay, so just to remind you, let's start with an equation first, right? I know that my current density is going to equal to current divided by area, right? The current is already known. So the main challenge here is to identify where the corrosion surface is, right? And the corrosion happens just in the inner surface, and of course, it only happens where we actually have the metal in direct contact with liquid, right? So in a sense, I need to estimate this surface area, okay? Now, in this course, you will have to remember some of the geometry equations, right? The surface area of this cylinder, right? And I'm going to actually draw it so we are all on the same page. So I have a cylinder, right? And I will have these two top and bottom, right? Which is going to be 2 pi r squared plus Now I need to take this circumference over this entire length, right? So that would be 2 pi r and the height, right? Or length, 2 pi r h. And so these are the pieces. And okay, now if I am to apply this knowledge to my particular problem, I know that I don't have to consider all of that area because to begin with, I don't have the ceiling, right? Because my water doesn't touch the ceiling, so I only have to consider the bottom. That means, and right away I'm going to be plugging in the numbers. So I'm going to put the current that we just estimated as 2.289 amp divided by, and then as for the area, right, I'm going to go with not 2 pi r squared, but only pi r squared, meaning that I will have pi times 25 squared, right? Diameter is 50. This is why I'm going with 25 plus 2 pi r 25 times. Now, when it comes down to the height, again, I only consider the height of the level of water, right? Which is going to be 16. And then the answer will give me 2.53 times 10 to the power minus 5 amp per centimeter squared, right? So that would be the two answers of the problem. I love questions like that. And during exam, I usually give something that does involve a little bit of geometry, where you have to visualize the process. Once you do that, the entire problem gets very, very easy. All right, let's solve a few more problems. The wall of a steel tank containing aerated water is corroding at a rate of 54.7 mdd. Okay. Now, mdd stands for milligram per decimeter squared per day. Okay. This is something that you would like to remember by heart because you would need it quite a bit. Now, just to remind you, 1 decimeter is equal to 10 centimeters, meaning that 1 decimeter squared is going to be 100 centimeter squared, right? So this is just the area. Now, how long will it take for the wall thickness to decrease by 0.5 millimeters? Okay, so how do we approach this problem? Perhaps I'm going to show you the easiest way to achieve that. One of the ways to do that is that I am given milligrams per decimeter squared per day. What I would like to do is that I would like to go from these units to millimeters, since the thickness of the wall is given in millimeters. I would like to jump to millimeters per day. Okay. And now that I need to find days, that should be relatively easy, right? Because I can get rid of millimeters because I know the thickness. I know that I'm given 0.5 millimeters. And if I know the rate, which is in millimeters per day, I can easily estimate the number of days, right? So, but how do I make this first jump, right? This specific jump. How do I get rid of my milligrams per decimeter squared, right? Because I'm gonna keep just millimeters and per day. Well, I would need to know density, right? Because that is going to be the way to make this jump, right? So the density of iron, and again, if you encounter something like that during an exam, you will be provided the density, you'll be provided more information than you need. And you just have to identify the information you need. So what I'm going to do is that I'm going to take my 54.7 milligrams per decimeter squared per day, right? And I'm going to divide it by the density, which is 7.87 gram per centimeter cube. Before I do that, I need to consider something that my milligram, right, because I have grams and grams, instead of having my milli, I'm going to put here 10 to the power of -3. And now I would like to get rid of my decimeter squared, and I would like to put here my 10 to the 2 centimeter squared, right? Because 1 decimeter squared is going to be the same as 100 centimeters squared, right? Now I'll be able to get rid of all the units except centimeters per day, right? This is what I will end up with. I'm gonna end up with 0.695 times 10 to the power of 4, and units would be centimeters per day, okay? Well, the rest is going to be relatively easy, right? The rest is going to be relatively easy because all I have to do now is that I need to take the given thickness, which is 0.5 millimeters, which is 0.05 centimeters, and I need to divide by the reduction in thickness per day, which is this number right here, right? Centimeter per day, and that will give me 719 days, okay? So as you've noticed, some of these problems would require either the knowledge of geometry a little bit, right? Or you have to get very comfortable with the units to be able to make these transitions, right? But as you saw earlier on the slide at the very bottom right in here, it says that the corrosion rate is expressed as weight loss per unit area per unit time. That was the problem where we had the MDD, right? Milligrams per decimeter squared per day, or a loss in depth per unit time, right? An example of such would be right in here when we had centimeters per day per unit time, right? Now let's see if we have one more example here, the last example for this section. A sample of zinc corrodes uniformly, meaning across the entire area, with a current density of, okay, so I'm given my current density, and it is in the aqueous solution. What is the corrosion rate of zinc in milligrams per decimeter per day? So I need to get to MDD. Okay, so I'm given amp per centimeter squared, and I need to get to MDD. All right, well, I'm going to start with this one, right? So I know it's going to be current density times area times molar mass times the time. And then here I'm going to have an F, and I'm given zinc. And the information that I have about zinc is that the molar mass, well, 2 electrons, right? And then perhaps the molar mass is going to be 65.38 gram per mole. I pulled that number from the periodic table. Okay, now let's plug in everything we know. We have 4.27 times 10 negative 10 to the power of -7 amp per centimeter squared, right? Times the area. Okay, well, since I need to find out the area in MDD, I can actually use right away the area of 1 decimeter squared, right? Because, oh, per decimeter squared. I just saw that there is a mistake on the slide. I'm interested in the rate of milligrams per decimeter squared. So decimeter squared is going to be the area that I'd like to take. And I know that decimeter squared is the same as 100 centimeters squared. Okay. Now, the molar mass is going to be 65.38 gram per mole, right? And time is going to be 1 day. And so I will convert it right away to the seconds, right? Which is going to be 24 times 3600 seconds, okay? Now I know that there are 2 electrons involved, and my Faraday's constant is 96,500 amp times second times mole. Now let me see what is happening here with the units, or perhaps I can even put the answer right away, 1.25, and now I'm gonna work with the units. Okay, so amp cancel out, right? Centimeter squared cancel out. Gram is left, right? And then mole cancel out, second and second cancel out. So as you can see that I arrived to the number of 1.25 grams, but this number is going to be identical to 1.25 mdd, right? I'm going from grams to the milligrams per decimeter squared per day. Why? Because because I did take into consideration, I know, okay, I see that it's not, I'm pretty sure that this math is milligrams, pretty sure. That means that I also need to do the conversion is I need to multiply it by 1,000 to go to milligrams because I just realized grams and grams. So I'm left with milligrams. Okay. So once again, once I'm doing this entire math, I end up with 1.25 milligrams. But I also know that the number in MDD is going to be identical to the same number. It's going to be 1.25 MDD. Why? Well, because in the calculations that I've done, the time that I considered was exactly 1 day, and the area that I plugged in was a 1 decimeter squared.